Module 2, Lecture B, Dictionaries and Files. By the end of this lecture, you will be able to use dictionaries to represent labeled process and material properties, read and write simple text files containing chemical engineering data, and combine containers to model structured engineering records. Engineering dictionaries. Property labels. In engineering, data becomes more useful when values are tied to clear labels. Dictionaries support this by pairing each value with a descriptive name, such as temperature or pressure. This makes data easier for people to understand and helps keep it organized for computation. In chemical engineering, clear property labels are essential because similar-sounding quantities can mean very different things. Flow rates may refer to mass, moles, volume, or individual components, and fluid properties like viscosity or pressure also have distinct uses. Storing data with meaningful labels helps prevent mistakes in calculations and makes the information easier for both people and computers to understand. Clear property labels make data easier to understand, maintain, and share. They should distinguish similar measurements while staying simple, such as naming an inlet temperature when both inlet and outlet temperatures are recorded. Good labels make records more self-explanatory and easier to manage in practical plant or lab settings. Python code. Property labels. Dictionaries pair clear engineering labels with their values, which helps avoid confusion about properties. In this example, they are used to store stream properties in an organized way. A feed stream dictionary stores key properties of a process stream using descriptive labels. In this example, it identifies the stream as the reactor feed and records its temperature as 85 degrees Celsius and pressure as 240 kilopascals. This makes the stream data organized, readable, and easy to access. The stream properties include a mass flow rate of 1,250 kilograms per hour and a liquid density of 920 kilograms per cubic meter. These values describe key flow and material characteristics and make the stream data easier to organize and use in calculations. This example shows how to read selected properties from a feed stream dictionary using descriptive keys. The stream name, temperature in Celsius, and pressure in kilopascals are each retrieved and stored in separate variables, making those values easier to use later. A new dictionary entry is added to record the pipe diameter as 3 inches, updating the stored information about the stream. Then, the dictionary's length is checked to count how many key value pairs it contains after the update. The code prints a brief summary of a dictionary record for a stream. It shows the stream name, then retrieves and displays the temperature in degrees Celsius and the pressure in kilopascals. It also reports how many property labels are stored, giving a quick overview of the dictionary's contents. The code goes through each label and value in the stream dictionary and prints them together. This shows every stored property in a clear, organized way. The line looks up the mass flow value in the dictionary using its descriptive label, then prints it in a sentence. This shows how labeled dictionary entries make it clear and precise to access specific stream properties. This script shows how a dictionary can organize engineering properties for a process stream using clear labels. It stores values such as stream name, temperature, pressure, mass flow, and liquid density, then retrieves selected values by their labels. It also adds pipe diameter, counts the stored labels, and prints a property summary. Overall, it demonstrates how dictionaries make labeled engineering data easy to store, update, and look up. Property lookup. Dictionaries are useful in engineering because they let you look up values by property name, such as temperature or pressure, instead of by position in a list. This is especially helpful in chemical engineering, where several related properties may describe one material or condition. Naming each value makes the data easier to read, check, and use, without mistakes from remembering the wrong order. In engineering, dictionaries match the way process data is usually understood, by meaningful labels rather than positions in a list. Engineers look up values using terms like pressure, density, or boiling point, which keeps the connection between each property and its meaning clear. As datasets grow, this label-based structure helps organize information in a way that preserves its engineering context. Using labeled property lookup in dictionaries makes engineering data easier to update and reuse. New properties can be added as projects grow without breaking existing lookups, because values are retrieved by meaningful labels rather than position. This keeps records clear, traceable, and less ambiguous during engineering analysis. Python code, property lookup. Dictionaries store values under meaningful property labels, making it easy for engineers to retrieve data by name. This example applies that idea to a stream record. A dictionary is created to store key process properties using clear descriptive labels. It records the feed stream temperature as 85 degrees Celsius, pressure as 220 kilopascals, and mass flow rate as 1.75 kilograms per second. This makes the values easy to access and manage by name. The feed stream dictionary is used to retrieve key properties needed for analysis: temperature, pressure, and mass flow rate. Each value is accessed by its corresponding dictionary key, making the data available for later calculations. Convert pressure from kilopascals to bars by dividing by 100, since 1 bar equals 100 kilopascals. Then find the residence factor by dividing the mass flow rate by the pressure in bars, giving the flow rate per unit pressure. This helps describe how the system behaves under different pressure conditions. The output summarizes key feed stream properties in a clear format. It shows the temperature in Celsius, pressure in both kilopascals and bars, and mass flow rate in kilograms per second, using consistent decimal formatting for readability. A property name is set to viscosity in millipascal seconds so it can be checked in the feed stream dictionary. The dictionary get method is then used to retrieve that value safely. If the property is missing, it returns not recorded instead of causing an error. The code uses the dictionary get method to safely retrieve viscosity, returning a default message if it is missing. It then prints either the recorded viscosity or that message. Finally, it calculates mass flow per bar by dividing the mass flow rate by the pressure in bars and prints the result to 3 decimal places. This script uses a dictionary to store and look up feed stream properties such as temperature, pressure, and mass flow rate. It converts pressure from kilopascals to bars, calculates flow rate per bar, and prints the key results in engineering units. It also checks safely for an optional viscosity property and returns a default message if it is not available. Labeled property lookup. Labeled property lookup means retrieving engineering values by meaningful names rather than by their position in a sequence. In chemical engineering, this makes properties like temperature and pressure easier to identify and use. Dictionaries support this approach by linking each label directly to its value, making data handling more intuitive and less error-prone. Using labels to look up engineering data makes information clearer and reduces mistakes. Instead of depending on the order of values, labels identify what each value means, such as molecular weight, boiling point, temperature, or pressure. This is especially important when similar properties appear for different materials or equipment, because labels preserve the engineering context and make the data easier to interpret correctly. Labeled property lookup makes engineering data easier to understand and share by using meaningful names instead of relying on internal order. Clear, consistent labels help team members and systems find the right values, especially as datasets grow. Descriptive labels such as inlet temperature rather than temperature reduce confusion and support more reliable analysis and decisions. Python code. Labeled property lookup. Dictionaries link clear names to engineering values, which helps avoid mistakes from relying on position alone. In this example, they make retrieving ethanol properties more readable and less error-prone. A dictionary is created to store key ethanol properties using clear descriptive labels. It includes ethanol's molecular weight in grams per mole and its boiling point in degrees Celsius, making these values easy to access later in the code. The code stores key physical properties of ethanol using clear descriptive labels. It records the liquid density as 789 kilograms per cubic meter and the heat of vaporization as 38.56 kilojoules per mole. This organization makes the values easy to retrieve and helps reduce data handling errors. Ethanol's properties are accessed from a dictionary using clear descriptive labels. The liquid density and boiling point are retrieved by their names, which makes the lookup easy to understand and helps avoid mistakes from relying on item positions. The dictionary get method is used to look up ethanol's viscosity safely. If the viscosity value is missing, it returns a default message saying it is not recorded, avoiding an error when optional data is unavailable. The output begins with a header for ethanol properties, then reports ethanol's density in kilograms per cubic meter and its boiling point in degrees Celsius. It also displays viscosity when available, or a default message if that value is missing. A feed stream dictionary is created to store key information about an ethanol process stream. It identifies the stream as the ethanol feed and records its temperature as 25 degrees Celsius, defining the basic conditions for processing. This code stores key properties of a process stream using clear labels. It records a pressure of 101.3 kilopascals and a total flow rate of 12.5 kilomoles per hour, making these engineering values easy to identify and retrieve. To get a specific value from a feed stream dictionary, use a descriptive label that matches the desired key, such as the total flow rate in kilomoles per hour. This lets you retrieve the value directly by name, making the code clearer and less error-prone than relying on positions. The code prints a clear label showing the flow rate of the ethanol feed stream in kilomoles per hour. It gets the stream name and flow rate, then combines them into a formatted message that is easy to interpret. This script shows how dictionaries can store and retrieve labeled engineering data for ethanol. It records key properties such as molecular weight, boiling point, density, and heat of vaporization, then retrieves values by name to make lookups clearer and less error-prone. It also handles a missing property, viscosity, by returning a default message instead of failing. A second dictionary represents an ethanol feed stream, using labeled fields to retrieve and print the stream name and total flow rate. Text file handling. Opening a text file connects a program to store data so it can either read existing information or record new information. In chemical engineering, this might involve data such as temperature or pressure readings. The file must be opened in the correct mode, because reading and writing are separate actions with different results. When working with files, choose the mode that matches what you need to do. Use read mode to access existing data, write mode to create new output while remembering it can replace old content, and append mode to add information to an existing file. Selecting the right mode helps protect data and keeps workflows clear and reusable. When working with files, make sure the file name and location are correct so the program can find them. Even small spelling or organization errors can block access. After using a file, close it to free resources and ensure any written data is saved. Careful file handling helps engineers work reliably with data from experiments, logs, and simulations. Python code, opening files. Text files let programs work with stored engineering data. Opening modes determine whether a file is read, written, or appended, while context managers help ensure files are closed safely after use. The script first stores the text file's name in a variable. This makes the file name easy to reuse later when the file is created, read, or updated, and it helps keep the code consistent if the name needs to change. The file is opened in write mode to create or overwrite a text file for feed stream temperature data. A context manager safely closes the file afterward, and UTF-8 encoding supports proper text handling. The file is initialized with a header and a first recorded temperature of 72.5 degrees Celsius for run 1. The code creates a small text dataset by writing feed stream temperatures for 2 runs. It records run 2 at 74.1 degrees Celsius and run 3 at 73.4 degrees Celsius, providing data that can later be read or extended. The file feedtemperatures.txt is opened in read mode, so its contents can be accessed without changing it. A with statement handles closing the file automatically, even if an error occurs. The read method then loads all the text into a variable for later processing or analysis. To add new data without deleting what is already in a file, open the file in append mode with UTF-8 encoding. Then write the latest observation at the end, such as run 4 with a value of 75.0. This keeps all existing data intact while adding the new measurement. The file named feedtemperatures.txt is opened in read mode with UTF-8 encoding, so its contents can be accessed safely without changing them. The readLines method then loads every line into a list of strings, where each item represents one line from the file. This makes it convenient to process the data line by line. After creating the file, the program prints a confirmation message, shows the first line as a quick preview, counts the total lines to verify the updated entries, and prints the final line as the latest measurement with extra white space removed. This script shows how to handle files in Python safely using context managers, which automatically close files after use. It creates a text file with a header and temperature readings, reads the contents, appends another reading without erasing the existing data, and then reads the updated file line by line. The output confirms the file was created, previews the data, reports the new line count, and shows the last recorded temperature. Reading text files. Reading text files is important in chemical engineering because many systems store data such as temperatures, flow rates, and compositions in plain text. A program reads these files by bringing the data into memory so it can be analyzed or combined with other information. To use the data correctly, you must understand the file's structure, whether it is designed for people to read or for software to process in a predictable format. Text files are often best read one line at a time because each line usually represents one record or observation. This keeps the data in order and makes problems like missing values or unusual units easier to notice. After reading each line, its parts should be separated, converted from text into the correct data types, and stored for later analysis, since numeric values must be interpreted properly before calculations. When reading engineering text files, focus on both data quality and context. Real files may include headers, blank lines, warnings, or missing values from sensor failures, so the reading process should handle these issues reliably. It should also preserve metadata such as units and identifiers because they give the data meaning. Careful file reading helps turn raw measurements into trustworthy information for model validation, experiment comparison, and performance monitoring. Python code. Reading text files. This topic covers reading small chemical engineering text files, turning raw characters into structured records, and storing labeled measurements in dictionaries for easy access and use. First, we define the file that will store the data, named reactor temperatures.txt. This gives the program a specific place to write the data and read it back later. It also lets us simulate how data might be exported from and imported into a real instrument workflow. A list is used to store lines of text that represent recorded data. The first line acts as a header, naming the columns for time in minutes, temperature in Celsius, and pressure in kilopascals. The following line gives one observation, with 0 minutes, 22.5 degrees Celsius, and 101.3 kilopascals, similar to a simple instrument data record. 2 additional reactor observations are stored as comma-separated text lines, like data exported by an instrument. They record measurements at 5 and 10 minutes, showing the temperature rising from 35.8 to 48.2 degrees Celsius, and the pressure rising from 118.9 to 136.4 kilopascals. The program opens a text file for writing with UTF-8 encoding, then writes several prepared lines of data to it. These lines represent sample output from an instrument, and using the write lines method saves them efficiently as a simple data log. We begin by creating an empty list to hold the data read from the text file. Each measurement will be stored as a dictionary, giving us a simple structure for collecting and organizing the records as they are processed. The file reactor temperatures.txt is opened in read mode using UTF-8 encoding, so its text can be read correctly. The first line is treated as the header row, cleaned of extra white space, and split by commas to create the column names used as keys for later data records. The code reads the data file line by line. For each line, it removes extra white space and separates the contents at each comma, turning the line into individual data fields for later processing. This code turns text data into numbers by building a record dictionary from the column names and the matching values in each row. Each value is converted to a floating point number because data read from a file starts as text, but numeric calculations require numeric types. The code builds one measurement record as a dictionary. It uses the pressure header as the key and stores the matching data value as a floating point number. This record is then added to the records list, so each observation is stored as its own dictionary. First, the program checks whether any records were loaded from the file. If none were loaded, it raises an error saying that no reactor measurements were found. This prevents the program from continuing with empty data and producing unreliable results. To summarize the reactor measurements, calculate the average temperature across all records, add the temperature values from each record, then divide by the number of records. This gives a concise overall measure of the collected temperature data. The output provides quick checks on the loaded data by showing the number of records, the column names, and one sample record as a dictionary. These checks confirm that the file was read correctly and that text values were converted as expected. It then prints the average temperature across all records, rounded to one decimal place, as a simple summary statistic. This script demonstrates how to read a small text file of chemical engineering data, such as reactor temperatures and pressures over time. It creates sample instrument-like data, reads each line into structured records with column names and numeric values, and stores them for analysis. It then reports the number of records, the columns, the first record, and the average temperature. Writing text files. Writing text files lets a program save data in a readable, shareable form that remains useful after the program ends. In chemical engineering, this can support records such as experimental temperatures or pump conditions. Clear labels, units, and context are important so others can understand the data without special software. Engineering data in a text file should follow a clear, predictable structure. Use a descriptive header, keep each row in the same format, and choose one separator, such as commas or tabs, for the entire file. This consistency makes the data easier to read, reduces confusion, and helps when importing it into spreadsheets, plotting tools, or other analysis software. When working with files, decide whether to create a new file, replace old contents, or add new data. Use overwriting for fresh results and appending for ongoing records. Choose numerical precision carefully. Always include units and close files properly so data is saved and resources are released. Python code, writing text files. Text files are useful for preserving engineering calculations, but they should include clear labels and units to avoid ambiguity. Using context managers helps ensure files are closed safely after use. A list is created to store measurement records from a small heat exchanger. Each record is a dictionary containing the time, temperature, and pressure values for a specific reading. This organization makes the data easy to access and work with later in the script. A dictionary is added to the measurements list to store one heat exchanger data point. It records the time as 10 minutes, the temperature as 48.5 degrees Celsius, and the pressure as 108.2 kilopascals. This structure makes the measurement easy to store and retrieve for later analysis or logging. Define a variable for the file name where the data will be saved. Use a clear, descriptive name that shows the file contains heat exchanger log information, making the data easier to organize and find later. The file is opened in write mode with UTF-8 encoding, using a context manager so it closes automatically when finished. The program then writes a title, identifying the file as a heat exchanger trial log, followed by column headers for time in minutes, temperature in Celsius, and pressure in kilopascals. These headings make the recorded data clear and include units to prevent confusion. The process goes through each measurement record and creates one line of output for it. Each line contains the time in minutes and the temperature in Celsius, with the temperature shown to one decimal place. This keeps the data consistent and easy to read in the output file. The code creates a formatted line from the measurement data, rounds the pressure value to one decimal place, and adds a new line so each record appears on its own line. It then writes that line to the file, adding the latest measurement to the log. To inspect the file's contents, open it in read mode using a context manager, so it closes automatically afterward. Specify the file name and UTF-8 encoding. Then use the readlines method to load all lines into a list. This makes the saved content easy to review or process further. The code confirms that the file was created, then announces a preview of the saved text. It prints only the first 5 lines, giving the user a quick check that the file content was written correctly without showing too much information. This script records heat exchanger measurements in a text file. It stores time, temperature, and pressure data, writes them with a header using UTF-8 encoding, and formats the numeric values to 1 decimal place. It then reads back the first few lines to confirm the file was created and the data was saved correctly. Structured records. Nested process records. A nested process record in chemical engineering groups related data inside larger containers, so each value stays connected to its meaning. For example, a reactor's identification, temperature, pressure, and streams can be stored together, making the process data easier to organize and interpret. This structure reflects how engineers think about process units as sets of connected properties rather than separate numbers. Nested process records help organize repeated engineering data by grouping related values inside larger equipment records. For example, trays in a distillation column or sides of a heat exchanger can each keep their own relevant details. This keeps labels tied to their values, making process data easier for both programmers and users to manage, understand, and trust. Nested process records help model engineering systems by keeping related data and its context together. They can combine information from sources like lab notes and simulations while preserving details such as sample location and conditions. This makes the data easier to save, compare, calculate with, debug, and extend as programs grow. Python code, nested process records. Nested records help keep process data organized by grouping related information together. Inner dictionaries can represent meaningful engineering groups, while lists can hold repeated structured records. A reactor process unit record is created using a dictionary. It includes a tag value, R101, which uniquely identifies the reactor, so it can be referenced and managed within the larger data structure. The code marks the reactor as running and records its operating conditions. It also sets the reactor temperature to 82 degrees Celsius, showing the current thermal state of the active process. The reactor conditions are stored in a nested data structure, with pressure set to 240 kilopascals and volume set to 3.5 cubic meters. These values describe the reactor's operating environment and capacity, while the structure makes the data easy to access and update. This code defines a feed stream entry for a process unit using a nested dictionary. The stream is labeled aqueous feed, and its flow rate is set to 1,200 kilograms per hour, indicating the material input rate to the unit. The feed stream includes a composition section that defines the mixture proportions. In this case, the feed is 72% water and 28% ethanol. Organizing the data this way makes the composition easy to access and adjust for process calculations. This part of the code stores the reactor's outlet streams as a list within the reactor record. Each entry in a list represents one outlet stream, such as the product stream, and can hold its own properties. This structure keeps stream data organized and easy to access for engineering analysis. The product stream leaving the reactor is set to a mass flow rate of 1,185 kilograms per hour and a temperature of 84 degrees Celsius. This code defines a dictionary for a reactor outlet stream called the vent. It records the stream's flow rate as 15 kilograms per hour and its temperature as 40 degrees Celsius. The dictionary keeps these key details organized so they can be accessed easily. This Python code closes a nested data structure for a reactor record. The square bracket ends the list of outlet streams, where each stream is stored as a dictionary, and the curly brace ends the overall dictionary. This organization keeps chemical process data structured and easy to access or modify. The reactor record is used to pull out three key pieces of information: the reactor's tag, the feed stream flow rate, and the first outlet stream flow rate. Together, these values identify the process unit and show how much material enters and leaves the reactor, supporting basic tracking and performance assessment. The reactor's temperature in the conditions data is updated to 85 degrees Celsius. The updated value is then retrieved and stored for later use, so future code works with the reactor's current operating condition. To check the mass balance, add the flow rates from all outlet streams to find the total outlet flow. This total is then compared with the incoming flow to confirm that mass is conserved across the system. The output presents a concise summary of a nested reactor process record. It identifies the reactor unit, then reports key operating and flow values, including updated temperature, feed flow, total outlet flow, and product flow. It also prints the mass balance error, comparing material entering and leaving the reactor to check whether the flows are consistent. This script uses nested dictionaries and lists to manage chemical reactor data, including operating conditions and stream flows. It reads key values such as the reactor tag and feed flow, updates the temperature, and adds the outlet stream flows to find the total output. It then reports the updated reactor summary and the mass balance error, giving a quick check of reactor performance. Nested records. Nested records help engineers organize complex data by grouping related information inside larger structures. For example, a chemical process stream can include operating conditions such as temperature and pressure, along with composition data such as mole fractions of different substances. This structure reflects how engineers naturally think about systems, making the data easier to manage and understand. Nested records make complex data easier to review, share, and extend. Instead of using a long flat list where details can be mixed up, nested groups keep each component's properties together, such as those for the feed, reactor, or product. This structure matches the engineering problem more closely, making the data clearer and reducing errors. Nested records help engineering workflows by keeping related data organized as it moves between calculations, files, and visualization tools. They can group stream properties, pilot plant measurements, or environmental details in structures that are easier to validate and expand. New properties or sample types can be added naturally, supporting a structured view of data with context and relationships instead of isolated variables. Python code, nested records. Nested records let dictionaries store other dictionaries, making it possible to group related engineering details. In this example, that structure is used to model process streams. A nested dictionary is used to represent a gas feed stream in Python. The outer dictionary identifies the stream as feed gas, while an inner conditions dictionary stores its key operating values, a temperature of 35 degrees Celsius and a pressure of 250 kilopascals. The stream is described by its flow rate and composition. Its flow rate is 120 kilomoles per hour, and its mole fractions are 0.82 for methane and 0.10 for ethane. These values define how much material is moving and the main chemical makeup of the stream. This code organizes stream quality metadata in a nested dictionary. It records that the quality information comes from a lab sample and that its status is checked, meaning the data has been reviewed and confirmed. This step adds carbon dioxide to the feed stream's composition and sets its mole fraction to 0.08. By assigning the value directly to the carbon dioxide entry, the composition dictionary is updated safely while keeping the overall nested structure unchanged. First, take the feed stream composition values to obtain each component's mole fraction. Then sum those fractions to confirm the composition is normalized, usually totaling 1, before using the data in later calculations. A product stream is represented with a dictionary that stores key process data. It identifies the stream as product gas and includes its operating conditions in a nested section. These conditions record a temperature of 28 degrees Celsius and a pressure of 210 kilopascals. The product stream is defined with a flow rate of 112 kilomoles per hour. Its composition is mainly methane at 88%, with ethane making up 9%. Together, these values describe the key flow and chemical makeup needed for further processing or analysis. This code adds quality metadata to the product stream using a nested dictionary. It records that the quality information comes from a simulator and that the status is estimated rather than directly measured. This keeps the stream's quality details organized and easy to interpret. A list is created to store two stream records, the feed stream and the product stream. Keeping these records together makes the data organized and easy to manage, so the application can access, iterate over, or process the full collection efficiently. The code summarizes key information from a set of stream records. It counts the available streams, reads the feed stream pressure, checks the carbon dioxide mole fraction, and verifies that the feed composition totals correctly after rounding. It also identifies the product stream's data source and confirms the flow units for the first stream, helping ensure the dataset is consistent and reliable. This script shows how to model process streams in Python using nested dictionaries. It defines feed and product streams with conditions, flow, composition, and quality data, then updates and checks the feed composition. The streams are stored together as a structured dataset, and the script prints selected values such as stream count, pressure, carbon dioxide fraction, composition total, data source, and flow units. Overall, it demonstrates how to organize and access nested engineering data efficiently. Structured samples. Engineering samples often combine identifiers, timestamps, locations, and measurements, so they need more structure than a single number. In programming, containers such as dictionaries and lists can represent records with named fields and repeated values. This keeps each sample's context and related measurements together, preserving the meaning engineers need from the data. Structured samples keep important data organized so it can be reviewed and shared without confusion. For example, wastewater sample records may include details such as collection point, date, and pH. Using a clear structure helps prevent errors like mixed units or unclear missing values, which is especially important in chemical engineering, where small differences can affect analysis. Structured samples help engineers organize related data as records and groups rather than isolated points. A trial, batch, or supplier group can contain measurements, notes, and other details in one flexible structure. Using dictionaries and lists in this way makes it easier to add new information, such as uncertainty or safety observations, while keeping the data model close to the real process or material system. Python code, structured samples. Use nested records to organize chemical sample data so each measured value stays connected to its label. This structure makes it easier to compare samples while preserving the context behind each measurement. An engineering sample record is created as a dictionary to organize key details about the sample. It stores a unique sample identifier, WW-001, and the sampling location, the influent channel. This structure makes the sample information easy to store and retrieve. The sample dictionary includes a conditions section that records environmental details from collection. It lists a temperature of 22.4 degrees Celsius and a flow rate of 180 cubic meters per hour. These values provide physical context for interpreting the sample's chemical analysis. This code stores a sample's chemical composition in milligrams per liter. It includes chemical oxygen demand set to 520, which indicates organic compound concentration, and total suspended solids set to 210, which indicates suspended particles in the liquid. These measurements describe the sample and support later calculations and comparisons. The code stores 3 repeated pH readings for one sample: 7.05, 7.10, and 7.08. These replicate measurements can be averaged later to give a more reliable pH value and reduce the effect of small measurement differences. The dictionary includes a field for flags that records the note that the field meter was calibrated. This kind of entry preserves important sample context, such as equipment status or data collection procedures, and supports traceability of the sample data. A second sample record is created with the same structure as the first, making later comparison and analysis easier. It has the unique ID WWW-002 and is labeled as coming from the final effluent location. The conditions record shows a sample temperature of 21.7 degrees Celsius and a flow rate of 172 cubic meters per hour. Together, these values describe the environment at the sampling location and help interpret any changes in the sample's chemical composition. This code represents a water sample's composition in milligrams per liter. It records 2 key measurements: chemical oxygen demand at 38.0, indicating organic compound concentration, and total suspended solids at 12.0, indicating suspended particle concentration. Together, these values help assess the sample's water quality. The code stores 3 replicate pH readings from the same sample: 7.42, 7.39, and 7.41. Keeping these measurements together makes it easy to calculate an average pH and check whether the readings are consistent. The sample record includes a flag indicating that the lab result has been reviewed. This helps show that the result was checked and verified as part of the structured information used to track the chemical sample. The code groups 2 sample records into one list, creating a simple container for their structured data. This makes it easier to work with the samples together, such as iterating through them, comparing values, or performing shared analyses. For each trial sample, we retrieve its list of replicate pH measurements. These values are then available for the calculations that follow. Calculate the sample's average pH by adding the pH readings and dividing by how many there are. Then, round the result to 2 decimal places and save it in the sample record as the average pH, giving each sample a clear summary of its pH measurements. To estimate treatment removal, compare the chemical oxygen demand, or COD, of the inlet sample with the COD of the outlet sample. These two values are used to calculate the percentage of COD removed during the treatment process. To find the chemical oxygen demand removal percentage, subtract the outlet COD from the inlet COD to get the amount removed. Then compare that amount with the inlet COD and convert it to a percentage. Round the final value to 1 decimal place for a clear result. The output begins with a header introducing structured sample summaries. The process then goes through each trial sample, retrieves its identifier, and prepares to display a concise summary of that sample's key attributes. The code gets the sample's collection location and retrieves its chemical oxygen demand, or COD, from the sample's composition data. COD indicates the level of organic compounds in the water, making it an important measure for assessing water quality. The average pH is taken from each sample's data and represents the mean pH measurement for that sample. A short summary is then printed for each sample, showing its ID, location, chemical oxygen demand in milligrams per liter, and average pH, so the results are easy to compare. The code reports the plant's chemical oxygen demand removal as a percentage reduction from influent to effluent. This gives a quick measure of overall treatment efficiency for the process being analyzed. The script summarizes 2 water treatment samples from the inlet and outlet, including operating conditions, chemical measurements, and repeated pH readings. It calculates each sample's average pH, then estimates how much COD was removed by comparing inlet and outlet COD levels. The output reports the key details for each sample and the overall COD removal percentage, giving a concise measure of treatment effectiveness. In this lecture, you learned to use dictionaries to represent labeled process and material properties, read and write simple text files containing chemical engineering data, and combine containers to model structured engineering records. In the next module, Module 3, we will go over none.
Thank you for your attention. See you all in the next lecture.